Okay, so for this part, the magnetic field, we have a solenoid. So this is a cross section through a current carrying solenoid, and you can see how the current is going out of the paper and into the paper like this. So it goes around in loops, and they do tell you this, but you can also refer this from the picture. You see that the tail of the arrow, so this means the current is going away from you, and here you see the tip of the arrow, so the current is coming towards you. So this is the correct direction of the current. And the first question is, sketch the magnetic field lines inside and at the ends of the solenoid. That's for 4 marks. And we can do it again very fast. So let me draw it also separately. So this is the top of the solenoid where the current is going into the page. And then at the bottom it comes out of the page. Like this. So this is the tip of the arrow. So this is the current. And you know inside the solenoid the magnetic field is constant. And by now we know how to draw constant fields. Parallel lines, equidistant, correct direction. And let me draw a few. So this is one. So you do a few lines like this. Outside the solenoid is like a bar magnet. So the magnetic field of a solenoid outside very much resembles that of a bar magnet, of a dipole. So you'll get lines like this. Just draw a few. And you don't have to close all the lines. Just draw a few lines. Now the direction. What's the correct direction? Well, if I follow the current with my fingers, then this is the magnetic field. So the current goes like this. The direction should be from right to left, towards the left. And you know that this is, if you think of this as a dipole, magnetic dipole, this would be like the North Pole and the South Pole. And that's it for 4 marks. Next one, a positively charged particle enters the solenoid along the axis. On the diagram, show the path of the particle in the solenoid. So this was C1, C2. I need to draw the path of a particle. So if the particle enters either from the left or from the right, then sine theta is 0. Theta is the angle between the velocity and the magnetic field. So either theta is 0 or theta is 180 degrees. In either case, you get 0 for the sine. So this means there is no magnetic force. B, Q, sine theta is 0. So the path is undeflected. So just follow the line, straight line like this. No deflection. And that's all they know, they want. Show the path of the particle in the solenoid, 1 mark. Continue, an electron is injected into a region of a uniform magnetic field of flux density 4 millitesla. So this is B. And the velocity of the electron is this, 1.6 10 to the 7. It makes an angle of 35 degrees to the magnetic field. D1, find the component of the velocity of the electron normal to the direction of the magnetic field. So we need to find this component of the velocity. Let me draw it here. So this would be D1. This is V. The magnetic field is like this. This is theta, 35 degrees. So I need to find V normal. Day 1, vector analysis, V normal is equal to V what? Sine or cosine? Sine theta. What was V? 1.6 times 10 to the 7 meters per second times the sine of 35 degrees. You need a calculator to do that. You don't need to memorize sines and cosines of strange angles like that. And you will get 9.2 times 10 to the 6 meters per second. And that's it. Next, describe making calculations where appropriate the motion of the electron due to this component of the velocity. 4 marks. So what kind of motion is this? Well, since the velocity has a normal component to the magnetic field, there will be a force. There will be a magnetic force, V cross B. So this is D2. So we'll have F, there is a normal component of the velocity of the magnetic field, and therefore there will be a force which is normal to this velocity and the magnetic field as well. So this means circular motion. Whenever you have a force which is normal to the velocity, you will get circular motion. And we can find the radius of that, because we know the centripetal force is the magnetic force. The only real force is the magnetic force. So we know that B times E, let me use this for the charge of the electron, so instead of Q times V, which is now this, is equal to centripetal force mv squared over r. So I will solve for r. What is r? R is mv normal be. And if I want to put numbers, then r would be mass of the electron 9.11, 10 to the minus 31 kilograms. V normal was found to be 9.2 times 10 to the 6. B is 4 millitesla, so 10 to the minus 3. And of course the charge of the electron is this. And if I do this with my calculator, we will get 13 times 10 to the minus 3 meters, 13 millimeters. Okay, so this is circular motion with that radius. This is actually called the cyclotron motion. Cyclotron. That's a more fancy word for that. Circular motion in the magnetic field. And that's it for that. There is a few more parts. One says find the component of the velocity along the direction of the magnetic field. That's another bonus point. So let me do it. Let me redraw the velocity v. That was b. That was the normal. We now need the parallel component, so we need this. Easy. This is now the cosine theta, so this is 1.6 times 10 to the 7 cosine of 35 degrees. Again, you need to have a calculator for that, and don't waste time with calculations. Okay, that's one easy mark. What was the next question? So that was 3. 4 says, state and explain the magnitude of the force on the electron due to this component of the velocity. Well, the angle between V parallel and as a vector the direction, and B is 0. So the force is 0 due to V parallel, or something like that. Put a few words to explain what you mean, that because there is zero angle between this component of the velocity and the magnetic field, from that component you get no force. You only get force from that component, from the normal. So, but you still have this velocity. This still exists. So the particle is moving in this direction, but there is no force due to that component. And finally, with reference to your answers in D, describe the shape of the path of the electron in the magnetic field. So this is an interesting phenomenon that is happening. The particle does circular motion because of one of the components, the normal, and it's also moving away due to the other component. So it does helical motion like this. So this would be like the V parallel. And the V normal will give rise to the circular motion. So this is a helical path, or a spiral path. And that's it. This is actually what the electrons and charged particles do in the Earth's atmosphere. If you think of the Earth as a big magnet, which is, to a first approximation, it is like a bar magnet. So this is the magnetic field of the Earth. It's like a dipole. And what happens from the solar wind is that you get all these protons and electrons. This is the solar wind, the plasma, and they get trapped into the magnetic field of the Earth. And they travel along these magnetic field lines, these like beads stuck or trapped into wires. And as they do, they will spiral like this. And they will collide with particles in the Earth's atmosphere, and will give rise to nice phenomena like the northern lights. Collisions with atmospheric particles will give colors, will give light. So you see the northern lights, or the aurora borealis. That's a very nice phenomenon, which goes to show you that physics is art. Thank you.